Welcome to Geology 108, the Age of Mammals. The Cenozoic Era, often called the Age of Mammals, spans the last 65 million years of Earth history. The extinction of the dinosaurs and ammonites 65 million years ago opens the world's ecosystems to new biological opportunities, which led not only to the rise of mammals, but also to an explosion of flowering plants. The Cenozoic is a time of shifting continents, climate change, and intense volcanism that forced a climate change from hothouse to icehouse, culminating in the cycle of glacial and interglacial periods of the Ice Age. Changing in ecosystems led to the evolution of humans in the savannas of Africa. After a period of unbridled expansion, humans have become a force of global change that surpasses natural processes. Now at the top of the food chain, without much competition or self-restraint, human activity causes changes in climate of such magnitude never seen for millions of years. Direct and indirect impacts of human activity is leading to a mass extinction event, quickly eradicating species that took 500 million years to appear. The history of life on Earth is very long and is dominated by the enormous stretches of time of the Archean and the Proterozoic that saw the emergence of prokaryotes and eukaryotes, respectively. These life forms constitute the basis of all life as we know it. The first presence of prokaryotes in the Archean is evidenced by stromatolites. Prokaryotes evolved photosynthesis and started releasing oxygen in their marine environment in the mid-Archean. Early oxygen reacted with iron in solution to form iron oxides that precipitated on the seafloor to form chert, type of sedimentary rock. Variations of oxygen levels in the oceans led to chert deposits of various colors and composition called the banded iron formations. When oxygen found its way to the atmosphere, began a mighty force of change that altered the planet forever. Slowly, bacterial life affected the composition of the atmosphere by increasing oxygen concentration. Atmospheric oxygen reacted with methane to form carbon dioxide, a less potent greenhouse gas. During the Precambrian, several snowball Earth events took place due to positive feedback between greenhouse gases, photosynthetic oxygen, ice albedo, and volcanism. Every transition from icehouse to hothouse led to mass extinction, followed by biological innovations and radiations. Eukaryotes evolved in the mid-Proterozoic with the biological innovations of respiration, sexual reproduction, and biological cooperation. This allowed the first animals to evolve, the so-called Ediacaran fauna. By the end of the Precambrian, the ozone layer formed, paving the way for plants and animals to spread to the land. The evolution of life in the Paleozoic is a story of invading the land. First, the coastline and swamps, then the continental interiors. The Paleozoic starts with the Cambrian radiation, an explosion of biodiversity marked by the apparition of animals with hard shells. For all of the Cambrian and Ordovician, life is entirely confined to the marine environment. During the Silurian, the first seedless, rootless plants appear on land, evolving from green algae. Arthropods follow suit, as their jointed legs and primitive respiratory system made them pre-adapted for life on land. Then plants evolve leaves and a vascular system that allow them to grow in size and capture more solar energy for photosynthesis. Vertebrates take a different path to the land, starting from an explosion of diversity of fish, jaws, and lobed fins in the Silurian. In the Devonian, fish evolved to amphibians, type of tetrapod with lungs and a permeable skin that rely on water for reproduction. By the Carboniferous, the major land ecosystems are swamps, dominated by insects, amphibians, and giant seedless plants. During the Carboniferous, dead organic matter is slowly converted to coal, a type of fossil fuel. Most of the known coal deposits formed during this period. Finally, two major biological innovations in the Carboniferous allowed ecosystems to expand to continental interiors. First is the evolution of gymnosperms, or naked seed plants, in the plant kingdom. The other is the evolution of the amniotic egg, an impermeable skin of reptiles. During the Permian, the continental interior of the Pangaea supercontinent starts to fill with conifers and reptiles. The Paleozoic ends with a mass extinction event called the Great Dying, caused by intense volcanism in the Siberian Traps, a large igneous province. The Permian-Triassic extinction is the most major extinction event in Earth history, with the disappearance of 95% of all species. The evolution of life in the Mesozoic is marked by the rise of dinosaurs, evolving from reptiles. During the Triassic, the first mammals and dinosaurs appear, and the gymnosperms become dominant. Dinosaurs have a different morphology from reptiles that allows bipedalism, that allowed dinosaurs to run faster and gave them better endurance compared to reptiles of the same size. An explosion of diversity of dinosaurs take place at the end of the Triassic, and dinosaurs become the dominant species by the end of the Jurassic. Birds, who share a common ancestor with dinosaurs, evolve at that time. The first flowering plants, or angiosperms, evolved in the Cretaceous about 160 million years ago, developing a special relationship with insects for pollination. Angiosperms also enclose their seeds in a fruit. With the first flowers, the landscape starts to assume many different colors. The Cretaceous, or the age of dinosaurs, end with another mass extinction event that coincides with different factors. Around the time of the Cretaceous Paleogene extinction, large variations of sea level are observed. There is also intense volcanic activity at the Deccan Trap in the Indian continent. But the extinction also coincides with a giant impact with an asteroid several kilometers wide. As a result of all these changes, all non-avian dinosaurs, all the large swimming reptiles, all the flying reptiles, and all the ammonites go extinct. The Cretaceous Paleogene extinction is followed by the radiation of other animals, the mammals and birds. During the Mesozoic, mammals were mainly small scavengers and plant eaters. Mammals occupied a narrow niche, living a nocturnal life and dwelling underground. They stayed rather small in size, probably to avoid the attention of dinosaurs. Mammals had many evolutionary advantages, such as warm blood, larger brains, and a more sophisticated reproduction system. But the dinosaurs remained the master of the food chain until they were forced to extinction. The Cretaceous Paleogene extinction event left the world devoid of organisms in many key ecological niches for both plants and animals. Repopulating these niches took millions of years, but flowering plants, birds, and mammals ultimately made the most of the opportunity. Within a few million years, angiosperms replaced the gymnosperms that dominated in the Cretaceous. The Cenozoic is divided into the Paleogene, Neogene, and Quaternary periods. The period encompassing the Paleogene and Neogene used to be called the Tertiary, but that term is now deprecated. The Paleogene period contains the Paleocene and Eocene epochs. The Neogene period contains the Oligocene, Miocene, and the Pliocene. The Quaternary is composed simply of the Pleistocene and the Holocene. The Pleistocene is a period of successive glacial and interglacial periods, also commonly called the Ice Ages. Humans evolved during the Pleistocene. We are creatures of the Ice Ages. We currently live in the Holocene, a period that started about 11,700 years ago, at the end of the last glacial period. The Cenozoic, also called the Age of Mammals, due to the expansion and dominance of mammals during this era. The Cenozoic is a time of dramatic changes characterized by many important tectonic events and a general trend of climate cooling from a hothouse to an icehouse. The Cenozoic's climate starts with a warm period called the Eocene thermal maximum, steadily transitioning to the Ice Age of the Pleistocene. Global cooling is associated with a change in the plant kingdom from the dominance of tropical rainforest to grassland. The cooling trend was also accompanied by a growth of mammals from the rodents of the early Cenozoic to the giant creatures of the Pleistocene. The rise of mammals was gradual in the Paleogene, with most mammals remaining small and rodent-like. Within 15 million years, such diverse forms of ancestral whales, bats, horses, and elephants had appeared to occupy the niches left vacant by the reptiles. The first primate ancestors also appeared during that time. Mammals consist in three groups: placentals, marsupials, and monotremes. Monotremes today are restricted to Australia and New Guinea, but originally spread through all of the southern hemisphere. These mammals are unique in still laying eggs. The young hatch out as tiny, helpless creatures and feed on their mother's milk until they are large enough to live independently. Marsupials, such as the modern kangaroos, koalas, and wombats of Australia, and the possums of the Americas, are reproductive intermediates. They do not lay eggs and produce live young, but these young are tiny and underdeveloped, and they complete their gestation in the mother's pouch. The marsupials dominated on the isolated island continents of South America and Australia, and many went extinct in South America with the introduction of placental mammals. Placental mammals are the most diverse of the three living groups. They produce young that are retained in a mother's womb much longer than is the case for marsupials, and are nourished by blood passed through the placenta. Placental mammals are remarkable for their diversity of sizes, from tiny shrews and bats weighing a few grams to the African elephant weighing up to 5 tons and the blue whale weighing perhaps 100 tons. Their ecological and geographic range is vast too, from desert living rodents to polar bears, and from bats to whales. The evolution of plants and animals in the Cenozoic is controlled largely by volcanic and tectonic events that slowly but dramatically change the global climate from a hothouse to an icehouse. The mid-Paleogene was marked by the Paleocene-Eocene thermal maximum, characterized by a 5 to 8 degrees Celsius global temperature rise. The onset of the warming event has been linked to volcanism and uplift associated with the North Atlantic igneous province, causing extreme changes in the carbon cycle. The rapid change upset oceanic and atmospheric circulation and led to a major turnover in mammals, coinciding with the evolution of the first primates. The Paleocene-Eocene thermal maximum is regarded as a geologically recent equivalent of climate change caused by rapid carbon dioxide emissions that helps us understand the ongoing climate change and mass extinction crisis. Since the Eocene, the climate trend has been global cooling. The first persistent ice sheets of Antarctica appeared in the Oligocene some 30 million years ago. Antarctica ice has waxed and waned for 10 million years, but complete reglaciation takes place in the Miocene 20 million years ago. Glaciation of Antarctica is caused by global cooling and continental drift. As Australia migrates northward, a circumpolar current surrounds Antarctica, isolating it from heat exchange with the surrounding oceans. Spreading ice sheet in Antarctica increased the albedo of Earth, starting a positive feedback cycle of global cooling. Accumulation of land ice also affects the global sea level, which eventually dropped by 200 meters in the Pleistocene, compared to during the early Cenozoic. Large sea level drops are important to create land bridge between continents and allow the migration of animals. As the trend of global cooling continues, the North Pole became permanently covered in sea ice by the mid-Miocene, some 15 million years ago, aggravating the positive feedback loop. Slowly, the Earth falls into an icehouse climate. The culmination of this process is the cycle of glaciation and interglacial periods of the Pleistocene. Lower temperatures change the environment from tropical forest to grassland and savannas ecosystems and turn the mammals into larger creatures such as the giant sloth, saber-toothed cats, mammoth, and mastodons of the Pleistocene. Tectonic activity, in particular continental drift, had a profound impact on the climate and biosphere of the Cenozoic. The end of the Cretaceous is marked by the formation of the last supercontinent called Pangaea. The breakup of Pangaea and of its subsequent largest continents, Laurentia and Asia to the north, and Gondwana to the south, paved the way for the current distribution of land masses on Earth. The drift of the resulting continents affected the global thermohaline circulation and the global climate, and provided geographic isolation for a number of new species to evolve. The breakup of Pangaea means the separation of the South America, North America, and Africa by the widening of the Atlantic Ocean, the separation of Australia from Antarctica, the migration of the Indian continent from Africa to Eurasia, and the eventual joining of North and South America at the Panama Isthmus. Australia started drifting away from Antarctica about 50 million years ago, sheltering marsupial forms of mammal life, such as kangaroos, that were outcompeted by placental mammals and went extinct on the other continents. Monotremes are still found in Papua New Guinea, a large island north of Australia. Let us discuss the important tectonic events of the Cenozoic. We start with Pangaea, the last supercontinent that regrouped all land masses in the Jurassic. Pangaea was surrounded by a global ocean called Pentalassa. At that time, there was no continent at the South Pole. By the Cretaceous, the last period of the Mesozoic, Pangaea is broken into two large continents, Laurasia to the north and Gondwana land to the south. Laurasia is a portmanteau for Laurentia in Asia. Gondwana land encompasses South America, Africa, Antarctica in the Indian continent, and Australia. Asia and Gondwana land are separated by a large ocean called the Tethys Sea. The end of the Cretaceous is marked by the so-called Cretaceous thermal maximum, a period of climatic warming characterized by large carbon dioxide levels. In the absence of ice sheets on land, sea level was high, and large portions of Antarctica and Europe were submerged by water. We start the Cenozoic 65 million years ago, at a time when Pangaea had already separated in the different modern continents. Africa is separated from North and South America by a growing Atlantic Ocean. Antarctica is already positioned on the South Pole. However, the Indian continent is still an island and on a collision course with Asia. Africa and Asia are still separated by the Tethys Sea, and the North and South American continents are widely separated. So many dramatic changes are yet to come. The Eocene marks the onset of the collision between India and Eurasia, which created the Himalayan mountains and is still ongoing today. The Tethys Sea between Africa and Eurasia is closing, leading to changes in global ocean circulation. The expansion of the Atlantic Ocean is compensated by the closing of the Pacific Ocean by subduction on the west coast of North America, leading to the growth of the Rocky Mountains. Many important tectonic events take place in the Oligocene 30 million years ago. The Indian-Eurasian collision created Earth's largest mountain range, the Himalayas, with profound impact on climate. The Himalaya mountains, formed with marine sedimentary rocks, limestone, such that we can find marine fossils at the top of the highest mountain. The closure of the Tethys Sea is associated with an extensive mountain range called the Alpine Himalayan Belt. It includes the Alps that resulted as a result of the collision between Africa and Eurasia, and the Zagros Mountains that resulted from the collision between the Arabic Peninsula and Eurasia. The collision between the Arabic Peninsula and Eurasia created the first land bridge between the North and South hemispheres. Meanwhile, Australia migrates away from Antarctica, which also completely separates from South America. The complete isolation of the continent allows a circumpolar current to form around Antarctica, preventing heat exchange with the surrounding thermohaline circulation. This exaggerated the cooling trend in Antarctica, resulting in the accumulation of thick ice sheets. The enclosure by land masses of the Arctic Circle led to an accelerated cooling of the high northern latitudes, leading to the formation of sea ice around the North Pole around 15 million years ago. Fast forward for another few million years, and another major tectonic event occurred. First, Australia collides with Southeast Asia, creating a new land bridge between North and South. Second, North and South America connect by land bridge at Panama 3 million years ago, allowing animal migration between the two continents. Africa and Eurasia were separated by a wide ocean called the Thesis. The closure of Thesis, accompanied with the collision between Africa and Eurasia, formed the Mediterranean basin, which is enclosed by the Arabian Peninsula to the east and by the Strait of Gibraltar to the west, leading to a drier regional climate. Waxing and waning of ice sheets during the Miocene affected sea level, leading to multiple desiccation events, meaning cycles of partial or complete evaporation of the Mediterranean Sea, called the Messinian salinity crisis. Tectonic evolution in the Cenozoic had immense impact on the climate and biosphere, enhancing global cooling and modulating animal migrations. The Cenozoic is the era when the continents finally moved into their current positions. Australia drifted north and collided with Southeast Asia. The Atlantic Ocean widened and South America connected with North America 2.8 million years ago. The Thetis Sea closed, leading to the collision between several continents and the formation of the Alpine Himalayan belt. India collided with Asia about 50 million years ago, creating the Himalayas. Arabia collided with Eurasia, closing the Mediterranean basin and creating the Zagros Mountains some 35 million years ago. The formation of mountains has important impact on regional and global climates. Mountain building is balanced by erosion. The chemical weathering of limestone occurs by the formation of acidic rain from the mixture of atmospheric water with carbon dioxide and by the dissolution of calcite by the acid. The byproducts are washed to the sea and the carbon dioxide becomes sequestered in marine sediments. The net result is a lower concentration of atmospheric carbon dioxide that reduces the potency of the greenhouse effect. As a result, mountain building is associated with climate cooling. The closure of the Thetis Sea therefore contributed to the global trend of climate cooling in the Cenozoic that culminated with ice ages in the Pleistocene. Having the large isolated continent of Antarctica over the South Pole allowed a circumpolar current to form over the last 10 million years that has blocked the approach of warm water and warm air, and thereby facilitated the formation of a long-term ice cap that now holds more than 2% of near-surface water on Earth. The presence of ice near the poles increased the albedo of the Earth, reducing the amount of solar energy that keeps the climate warm. Ineluctably, the Earth plunged into a new icehouse. Since the Pleistocene, 2.5 million years ago, Earth's climate alternates between glacial and interglacial periods. Though not as extreme as the earliest Noble Earth episodes, these repeated ice ages were accompanied by drastic drops in sea level by a couple of 100 meters. Ice bridges linked Asia and North America, allowing migrations of all manner of mammals, including mammoths, mastodons, and eventually humans, to the New World. Humans, together with chimpanzees, gorillas, and orangutans, are a primate species, part of the family Hominidae. Humans descend from a long history of mammal evolution. Primates arose between 85 and 55 million years ago from small terrestrial mammals that lived in the trees of tropical forests. Primates were well adapted to this environment, including large brains relative to body size, visual acuity, and color vision. Monkeys evolved between 60 and 40 million years ago during the Paleogene. Then, apes, which are tailless, evolved into many species about 20 million years ago in the Miocene. There are two extant species, meaning still alive, of apes: the gibbons, or lesser apes, and the hominids, or great apes. The great apes appeared between 20 and 15 million years ago and include the orangutans, gorillas, chimpanzees, and humans. Between 8 and 4 million years ago, the gorillas and the chimpanzees split off from the evolutionary line leading to the humans. Gorillas, chimpanzees, and humans share a common ancestor. Hominids, the name for human-like primates, started in Eastern Africa about 3.5 million years ago. Hominids appeared at a time of environmental change from jungle to savanna, probably caused by changes in Indian Ocean circulation. Our bipedal ancestors, like the Australopithecus, had an advantage by covering ground more easily in a more open environment compared to their non-bipedal evolutionary cousins. It is from this lineage that humans evolved, using endurance running as a means to acquire more resources and possibly even hunt. This can explain many uniquely human features, from our long legs, strong Achilles, lack of lower gut protection, and our wide range of running efficiencies. The earliest documented representative of the genus Homo is Homo habilis, which evolved around 2.8 million years ago from Australopithecus and is the earliest species from which there is evidence for the use of stone tools. During the next million years, a process of rapid encephalization occurred, and with the arrival of Homo erectus and Homo ergaster, cranial capacity doubled. Homo erectus and Homo ergaster were the first to use fire and complex tools, and were the first of the hominin line to leave Africa, spreading throughout Africa, Asia, and Europe between 1.3 and 1.8 million years ago. Homo sapiens evolved between 800,000 and 300,000 years ago in Africa and migrated out of the continent some 50,000 to 100,000 years ago, gradually replacing local populations of Neanderthals. When Homo sapiens escaped from Africa, the global human population was just 50,000 individuals. Until about 12,000 years ago, at the beginning of the Holocene, all humans lived as hunter-gatherers. The agricultural revolution, or Neolithic revolution, started about 10,000 years ago in Mesopotamia, and independently in Mesoamerica about 6,000 years ago. Access to more food led to the formation of permanent human settlements, the domestication of animals, and the use of metal tools for the first time in history. Agriculture and sedentary lifestyle led to the emergence of early civilization, the development of urban development, complex society, social stratification, and writing about 5,000 years ago. From the Bronze Age to the Middle Ages, the human population grew from 5 million to 500 million individuals. The scientific revolution that started symbolically with the invention of the printed press and was championed by scientists like Copernicus, Galilei, Newton, Descartes, and Spinoza paved the way for technological progress that would forever change the relationship between humans and nature. In the span of less than 300 years, the population doubled from 500 million to 1 billion people. The next expansion was fueled by the invention of the steam engine and the discovery of a fossil fuel that was waiting mostly untouched since the Carboniferous period. Mining coal fueled the Industrial Revolution that brought new modes of production and transport. This was followed by the Green Revolution, which is industrialization of agriculture. With prolific production of food, the population grew more than exponentially, reaching more than 7 billion people today. The pace of runaway expansion keeps accelerating due to positive feedback involving technology, access to more food and better medicine, and access to new forms of energy, like fossil fuel and nuclear fission. Human population growth and industrialization has led to environmental destruction and pollution, driving the ongoing mass extinction of other forms of life called the Holocene extinction or sixth extinction, seeing the extermination of countless species that took 500 million years to appear.